Welcome back. We are in module 2 lecture 3 and here we will talk about the ion exchange applications. In the earlier lectures we have seen that what is the ion exchange chemistry, what are the ion exchange reactions, how we can calculate the fraction of ions present in the solution and present on the resins. We have also seen that how we can calculate the ion exchange capacity. And we have also talked about that how the regeneration can be performed, what is the selectivity coefficients. So now today, after gaining these concepts, we are going to talk about what are the various applications of the ion exchange. When we talk about the ion exchange applications with regards to the water or the wastewater, so there are mainly three things that comes into our mind. That is, first of all, is the nitrogen control that is required, that is the removal of the ammonia or removal of nitrate, which can be performed by using ion exchange resins. Similarly, we can talk about the water softening, which is a very common application of the ion exchange. And lastly, we'll talk about the removal of the heavy metals, particularly the removal of heavy metals which are present in the electroplating path. And then we will talk about whatever the concepts we have gained till now, how we can apply it for solving the numericals or for calculation of different parameters of the ion exchange. So when we talk of the ion exchange applications, nitrogen control is one of the most important application that comes to our mind. So nitrogen control in wastewater treatment, it involves the removal of ammonium ions and nitrate ions from the wastewater stream, as we are talking of the nitrogen here. So synthetic ion exchange are preferred because they are more durable, but there are certain natural resins like clinoptilolite, which is a zeolite, which can be used for the ammonia removal because the clinoptilolite is effective, cost efficient, and has got a very high affinity for ammonium ions than in comparison to other materials. So the regeneration of cryptolite use calcium hydroxide. So calcium hydroxide mainly is used so that we can convert ammonium ions into ammonia due to high pH, as the ammonium ions gets converted to ammonia gas at high pH. So we use lime calcium hydroxide so that we can increase the pH and we can convert the ammonium ions into ammonia gas so that it can be removed by air stripping process. But the main challenge here lies that the formation of calcium carbonate crystals takes place in the zeolite exchange bed, and this can be removed by backwashing. So we have to employ backwashing so that these carbonate deposits which are there in the filter bed, they can be removed and we can ensure a efficient operation. So we can see here that the secondary effluent which comes from wastewater treatment, so it goes into the filtration first of all. So we filter this secondary effluent so that the suspended solids they can be removed, and then this filter can be backwashed later on. So the waste basically is taken for proper treatment further, and then it passes through the carbon adsorption column. So this carbon adsorption column is used so that we can remove the organics which are present in the wastewater so that they may not impact the zeolite that we are using for our nitrogen control. So here we can see that the waste is coming out from here and the water which gets treated after the carbon adsorption. So we can see here that the filtration and the carbon adsorption, so they are just acting like a pre-treatment for the secondary effluent process. After the carbon adsorption, so the water or the wastewater, it goes into the zeolite exchanger here. So there can be certain, after filtration also we can bypass some of the water so that it can be taken to the zeolite exchange depending upon the amount of organics which are present in the wastewater. So this zeolite exchanger, basically what it does, that it exchanges the ammonium ions because it is highly selective for ammonium ions. So these ammonium ions are exchanged here, and the water which now becomes free from this ammonium ions, the treated effluent, it goes out for the further disposal. And here we can see that when we are backwashing it, and we are also not only backwashing it, we are also basically passing the lime here so that whatever the calcium carbonate precipitates that are formed inside this zeolite exchanger, so they may be removed. So here lime is passed so that whatever the ammonium ions which are present here, so they can be converted to ammonia gas, and this ammonia lead in water then is goes to a stripping tower, the air stripping tower, where the ammonia can be removed by passing air from the bottom, and from the top the ammonia lead in water is passed and air is passed from the bottom, so that the air and ammonia basically are removed from here and they go to the acid scrubber for the further treatment. And here we can also see that we are backwashing the filter so that whatever the particles of calcium carbonate crystals that are formed, so they can be removed from our zeolite exchanger. So that's how the treatment of ammonia takes place, by using zeolite, which is clinoprololite, and this clinoprololite is very effective in removal of ammonia. So then we come to the nitrate removal, which is another form of nitrogen that can be present in the water. So when ammonia basically gets oxidized, so it gets converted to nitrate, and nitrate also basically we cannot put nitrate directly into the wastewater. We have to remove the nitrate from the wastewater so that the nitrate does not impact the aquatic life. So the conventional synthetic ion exchange resin, they face the challenge when removing nitrate from the water, because they are having very low affinity for the nitrate in comparison to sulfate. So which limits their capacity to effectively remove the nitrate. So we know that the wastewater not only contains nitrogen, that is nitrate, but it may also contain sulfate when we are having water which is coming out from the treatment units like aerobic treatment units like activated such process. So when it comes out, so the oxidation may convert not only in the nitrate, ammonia into nitrate, and sulfide into sulfate. So the sulfate, if they are present, so then there is a problem with the removal of nitrate, as sulfate now is having a higher affinity towards the resins, and the nitrate is basically displaced and sulfate is basically taken on to the resin. So it hampers the removal of nitrate from the wastewater. So this phenomena is known as nitrate dumping, where resin is having the lower affinity for nitrate over sulfate, and sulfate displaces the nitrate onto the resin, leads to the release of nitrate, and that's why it is called nitrate dumping. Now this generally happens, this is more, we can say, prominent when we are having the sulfate present in excess of 25% of the total concentration of sulfate and nitrate. If it is the sulfate is more than 25% of the total concentration of sulfate and nitrate, so then this problem may arise more. So this means that we need to have a certain resins which have higher affinities for nitrate, so that the selective removal of nitrate can take place. So when we deal with the wastewater which is having a very high sulfate concentration, so then we require a resin which can selectively remove nitrate over sulfate. Okay. Such type of performance of nitrate selective resins may depend upon the composition of the treated wastewater. Right? It will also require that we have a certain pilot scale testing to be done, so that we can see that what is the concentration of nitrate over sulfate which can be removed from the wastewater. So such type of selective nitrate resins are example tributyl amine or triethyl amines. So they can be used for selective removal of nitrate from the wastewater. So then another application which we call it as a very common application for the ion exchange column is to demineralize the water. That is, not only it removes the cations in the column, but it also removes anions in the column, and this water is known as deionized water or demineralized water. So it is free from all the ions. So if we are targeting only water softening, that is if we only want to remove the cations causing hardness like calcium and magnesium, then we can go for only a cation exchanger column. But if we want to demineralize the water, that is if we want a water which is pure H2O only, so then we go for two columns here, that is first is the cation exchange column, and then we take it to the anion exchange column, so that we can get a water which is free of any ions. For example, you can see here that when calcium leaden water, it comes in contact with a resin which is having H plus as functional group. So the calcium is basically, it replaces H plus ions, and H plus ions goes into the water. Similarly, magnesium is also removed by using RH plus as a resin. So this means that H plus ions are basically exchanged by the cations which are present in the water. So the equivalent amount of H plus goes into water. Now after this, we take the water to an anion exchange resin where all the anions which we want to remove, so they are basically replaced by an equivalent amount of hydroxide ions which are released into the water. You can see here that chloride basically replaces the OH minus ions. Similarly, then sulfate is there, it replaces the OH minus ions. So OH minus ions goes into the water. So we are having H plus ions and OH minus ions now in the water, which have been passed through the cation exchanger and then the anion exchanger. So what we get is a pure H2O, right? So this is known as a ion-free water or deionized water or demineralized water. So we can see here an example here that we are having calcium, magnesium, sodium, and then we are having bicarbonates and chlorides in the water. These are the major cations and anions present in the water. As we take this raw water to a cation exchanger here, right? So this cation exchanger, all the H plus ions basically they are exchanged by calcium, magnesium, and sodium ions, and we get in the water only H plus ions and the other anions which are present in the water. Right? After this, we take it to a anion exchanger where now whatever the anions are present, that is bicarbonates and chloride, so they are exchanged by OH minus ions. So we what we get here is a product which is called a demineralized water, that is pure H2O. Right? And then basically we can take it to a degasifier and a storage tank where we can store this type of treated water, and this can be used for various purposes where we need a highly pure uh, water, demineralized water. And then the acid regenerant can be used to regenerate the cation exchanger, and alkali regenerant can be used for regenerating the anion exchanger. So here also we can see that this is for the softening process only. It can be called as softening process also, or we can also call it as a demineralizing process, where we are having the hard water. So it is basically getting passed through a cation exchange resins which are there on a bed of gravel, right? So these are the gravel bed. These are the resins which are there in the column. This is passed here, and the water goes to an anion exchanger where again we are having anion exchange resin which are there on the gravel bed, and later we get a water which is soft water, or we can say it as a demineralized water also, right? And here we are having the regenerant solutions which are again put after the service cycle is over. Then we regenerate the resins, that is cation exchange resins and anion exchange resins, by using acid or alkaline regenerant so that the next cycle can start. So then there is another important application of ion exchange which is known as the metal removal. Now metal removal is very important in the system where basically we are having lot of metals going into the wastewater. So for example, the municipal wastewater may not contains very high amount of metals in it, but it is there in the industrial wastewater. So when we talk about the industrial wastewater, then it is very necessary that we remove the metals which are there, which are produced from the industries, before it goes into the municipal sewer system or before it goes to the treatment plant. This will prevent the accumulation and toxicity of these metals in the environment. So it is very necessary that when we are putting our industrial effluent into the municipal sewer systems or any type of sewer systems which are dedicated also, so that these metals can be removed from the wastewater for going to the treatment plant. So here we use again ion exchange process is used for removal of metals in various industries like metal processing, like electronics manufacturing, metal plating, pharmaceuticals, laboratories, vehicle service shops. So where here we find a number of metals which comes from various processes which are used, and it goes into the water and it becomes wastewater with a very high metal concentrations. So it is very necessary that we remove these metals before we discharge the waste or we take the waste to a treatment plant where it is possible that these metals may not be removed during the conventional treatment processes. So industries with fluctuating metal concentrations, so they may require flow equalization so that the ion exchange becomes feasible. In the sense that if we are having a fluctuating flow of the industrial flow which is coming out, so if we are putting it, the different flows are being put onto the ion exchange column, so it is possible that they may not work as basically we have designed it for a particular type of flow. So it is very necessary that a flow equalization to be done so that we can put a known amount of flow to the ion exchange column so that our ion exchange process becomes feasible. As we have also seen that if the flow becomes lesser or flow becomes higher, then it impacts the operating capacity or the exchange capacity of the resin. It can be said that the ion exchange process can be costly. So if we want to make the ion exchange process economically viable, then we have to focus on the removal and recovery of the valuable metals from such streams. So ion exchange process is highly dependent on the pH. So if we are using strong acid or strong base resins, so it can be used for a number for a different ranges of pH for the entire range of pH. But when we are using weak acid or weak base resins, so this will also depend upon the pH of the solution that we are treating. And similarly, the pH also affects the metal species, that in which form they are present depending upon the pH. And this impacts the interaction between the ions and the resins in the sense that the pH affects the metal species, pH also affects the efficiency of the resin. So depending upon the pH, the interaction of ions and resin will also be impacted. And then there can be several factors which impact ion exchange application for removal of heavy metals. For example, operating conditions, the temperature, right, ionic species, and the chemical background, influence of the selectivity of the resin. So these all factors, they impact the resin, as we have also discussed the previous lectures. Additionally, the presence of oxidants, the particles, the solvents, the polymers, they also can impact the performance of the ion exchange resin. So it is very, very important that we go for pre-treatment or the wastewater which we are putting onto the ion exchange column, so that these species, if they are present, so they can also degrade the resins which are used for our ion exchange process. And the management of the generated regenerate. So when we are basically having the regeneration process, so regeneration process may again lead to the concentrated solutions of the metals or other forms. So we also have to look for the management of the generated regenerates so that we can treat it properly and then we can dispose it off. So we can see here a very important example for the removal of the chromium. So it can be applied for electroplating bath solution. We are having a electroplating wastewater coming which contains a number of metal ions as well as the chromate which is used for the electroplating bath solution. So it is passed through a cation exchanger here so that whatever the metal ions they are present, so they can be exchanged here and we get a water which is now only laden with the chromate. Okay. And this cation exchanger then is regenerated by using H2SO4, right, as we have already discussed. So then what happens that metals sulfate basically comes into the effluent as the H plus ions are not now exchanged by the metal ions, and metal ions goes into the solution and then it can be taken for the further treatment. Okay. Similarly, this chromate then goes into the wastewater. So this chromate is now passed to the anion exchanger where the chromate is now exchanged with the OH minus ions, right? And we get a water which is free from these metals as well as the chromate solution. And now it is now regenerated by using sodium hydroxide. So this sodium hydroxide, the chromate ions basically are replaced by OH minus ions, and sodium chromate goes into the solution. Now this regenerant, the waste regenerant solution is now again passed through a cation exchanger. So where this sodium is now exchanged by H, H plus ions. So now it is removed as H2CrO4 and this can be used for the electroplating bath solution. That's how we can recover the chromate for our further applications in the electroplating bath, right? Similarly, now this cation exchanger can again be regenerated by using H2SO4 and similarly sodium sulfate results from here and this can be again taken for a further treatment case. So that's how we can get rid of not only the metal ions, but we can also get rid of the chromate, or we can not only get rid of chromate, but we can also reuse the chromate, which is a very, very costly chemical, and it is also toxic to the environment also. So if we are reusing it, so then we are also saving our environment from the disposal of chromate into the environment. As you all of you know that the chromium 6 can be highly toxic, as well as it can cause cancer also. So then after the application, we should also focus on the operational conditions, where the use of regenerant and restorants, which can not only remove the inorganics, but they can also remove the organic material from the resin. So we can use a certain regenerants and the restaurants, so they remove the inorganic material from the spent resins, as well as they will also remove the organic material which is trapped by the ion exchange resin columns. So we can use sodium hydroxide, HCl, or methanol or bentonite, so that we can remove the organics which are present in our ion exchange resin, which are used after the service cycle. Okay. So here we generally find that this ion exchange process may have a limited use because of the extensive pre-treatment that we have to do. Similarly, it will also depend upon the life of the ion exchange resins and the complex regeneration system, which also limits its use. So we have to go for a pre-treatment process, right? Similarly, the ion exchange resins are also having a certain age, right? They degrade with time, so that is also basically limits their application, as well as the complex regeneration system that is employed during the use of the ion exchange process. So that may also limit the use of ion exchange process. But when we are using it, so then we have to see that the higher total suspended solids may lead to the clogging and loss of the head, and it can also lead to the inefficient operation of the ion exchange treatment process. So this needs to be treated. So that's why we need a pre-treatment whenever we are going for an ion exchange process, so that our ion exchange process becomes more and more efficient. Similarly, organics which are present in the wastewater, they may also bind to the resin. So that also should be need to be removed. For example, we have seen in the previous slides where we are talking about the treatment of the ammonia, right? So there you have seen that we have gone for the filtration, and then we have gone for the carbon adsorption. So this is required so that we can remove the total suspended solids, and this is also required so that we can remove the organics which are present in the wastewater, which otherwise may impact the ion exchange process. So this means that the pre-filtration is required, and we can also use a certain scavenger exchange resins, so that the organics which can pose problem to the ion exchange column, so that can be removed from the water or the wastewater. So these are the things that we need to consider before we go to the ion exchange process. So now let us take an example here. So we are having a column study is being conducted so that we can determine the capacity of the ion exchange resins, right? So in this study, we are using 0.1 kg of the resin, which was warmed, washed with NaCl until the resin is in the form of RNA plus, right? And then the column is washed with the distilled water so that we can remove the excess chloride ions which are there in the resins. And then the resin was titrated with a solution of calcium chloride, right? And the concentration of chloride and calcium are measured. So we can see here that the concentration of chloride and calcium are measured, and it is written here, which are passing into the throughput volumes which are passing through the ion exchange column. And then we have to, using this data, we have to find the exchange capacity of the resin, and we have to also find out the volume of the resin that is required so that we can treat a 4000 cubic meter of wastewater which contains 18 milligram per liter of ammonium ions. And take the density of the resin is also given here. So how we can do this thing? So we first of all we'll draw the two curves which are the normalized concentration of the chloride and the calcium ions which are there in the throughput volume. So because normal concentration means that is the concentration which is coming out of the effluent divided by the initial concentration that we have put onto the ion. So basically C by C naught will ultimately become equal to 1, right? So then we see that if we want to find out at C by C naught equal to 0.5, so we can find out that what is the throughput volume that has gone here. For example, here the 22.1 liters is totally required for at the normalized concentration of 0.5. Similarly, the throughput volume required for the chloride ions is around 7.5 liters. So we can find out the exchange capacity by the throughput volume that has been passed. So we are talking about in terms of calcium ions, because we want to find out the exchange capacity for the cations. So this is the throughput volume required for the calcium removal, and then C naught is the initial concentration of the calcium that we have put, and R is the resin amount of resin that we have put into the column. So we are finding out the concentration at the capacity at C by C naught is equal to 0.5. So we can find out the total volume that is there. So 22.1 minus 7.5, because 7.5 represents the chloride ions and 22.1 represents the calcium ions which are applied to the column, and this is representing the equivalent concentration of our calcium ions that we have put onto the column, that is 40 milligram per liter we have put onto the column. So this is equal to around 2 milliequivalents per liter. Okay. And similarly 0.1 kg of the resin we have put. So by calculating we can find out that the capacity, the exchange capacity at C by C naught is equal to 0.5 is around 292 milliequivalents per kg of resin. Okay. So now we want to treat water which is having 18 milligram per liter of as ammonium ions. So we know that the concentration of ammonium ions in the solution that we need to treat is around 1 milliequivalents per liter. So the required exchange capacity comes out to be around, for the ammonium ions, it comes out to be around 4 into 10 power 6 milliequivalents, because we are passing a water which is around 4000 cubic meter. Okay. So this means that around 4 into 10 power 6 milliequivalent of ion needs to be exchanged, and we know that our the resin capacity is around 292 milliequivalents per kg. So we can divide the total ions that we need to remove, divide by the exchange capacity. So this gives us the total weight of the resin that we require for treating 4000 cubic meter of water which is laden with around 18 milligram per liter of ammonium ions. Right? Similarly, we know the density of the resin, so we can also calculate that what is the volume of the resin that is required for the treatment of ammonium ions. Okay. So the required volume of resin will be usually around 1.1 times 2. This is actually the volume of the resin which we have got theoretically, but we generally take it 1.1 to 1.4 times based on the exchange capacity. So we take it higher so that we can have a factor of safety into consideration. So now we also discuss the exchange capacity, that is also known as the operating exchange capacity. So here we are having a solution which contains uh, calcium ions here in this case, right? And these ions are being put onto the column, which we can see that here we are having a breakthrough curve. That is, so we have to compute the operating capacity of the cation exchange resins, right? And the breakthrough curve is given here, which is shown in the figure. The resin column is required to treat the total hardness of around 5 milliequivalents per liter, and the volume of the resin in the column is around 10,000. Okay, so we need to treat it to a point where we are having zero point 0.4 as C by C naught, okay, concentration. So we can see here that the area under this curve, right, from this point to this point, will give us the total capacity till C by C naught is equal to 0.4. Right? So we have to now set the intervals. For example, we can see from here that the first interval that we take is 0.05, that is yt here is C by C naught equal to point at 0.05 here, that is 0.05. So the volume is nearly 1200, right? So this total volume into this the concentration, the equivalent concentration, or we can say the fraction of the concentration. So this will give us the leakage till this point. Okay. We can see that 0.05 into 1210 liter that is passed till this point. So this gives us a value of around 3.5. Similarly, we make another strip where we are taking it from 0.05 to zero point 0.1. So the middle point is 0.075. So we take this as 0.075 as the average of C by C naught into the volume, that is this minus this volume. So we can see here that the volume is 1280 till this point and minus 1210. So 70 liters here. So this gives us a value of Y into V, right, equal to 5.3. Similarly, then we can take the next strip here. That is, the next strip represents from 0.1 to 0.2, right, and the average value is 0.15, right, and we multiply it by this volume, right? So this volume is around 1440 minus 1280. So this gives us 24. And similarly, we can take the middle of the next strip as 0.25, right, here, and 0.35 here, and the volumes corresponding to these strips, that is delta V, delta V1, delta V2, delta V3, delta V4, and delta V5 represents the volume that is there corresponding to these strips that we have considered. Okay. So this gives us around 154.8 as YT, summation of YT into VT. So this will be the we can say the amount of calcium that will be eluting from the column. So we can see that the total capacity, the operating capacity of the resin corresponding to C by C naught equal to zero point 0.4 will be equal to the amount of the resin, sorry, the hardness that we are putting here, that is 5 milliequivalents per liter of hardness is being put here, and 1660 represents the total amount of we can say the volume that is put onto the resin, right? Okay, so this is 1660 divided by 10,000 and minus the leakage that has happened during this process. So this represents the leakage that has happened during this process, and we can say that this is equal to around 0.75 milliequivalents per ml of resin. Calculate the operating capacity corresponding to this C by C naught is equal to 0.54. Okay, so that's how we can calculate the operating capacity of the resin. Now we come to another example where we see that we are having two types of wastewater here, that is wastewater A and wastewater B, which are having different concentrations of cations and anions here. So we are mainly concerned with the anion concentration because we are removing here the nitrate, right? So with sulfate and without sulfate. So you can see the first wastewater where we are having the sulfate present in the wastewater, sulfate not present in the wastewater, whereas in the second part we are having sulfate present in the wastewater, right? So we have to determine that what is the maximum amount of water that can be processed per liter of the strong base anion exchange resin with a exchange capacity of 2 equivalents per liter. So here, first of all, we have to calculate the selectivity coefficient. So we will be calculating the selectivity coefficients depending upon what amount of ions are present. For example, if we see the wastewater A here, so wastewater A contains mainly bicarbonates, right? It contains chlorides, it contains nitrate. Okay. So we have to calculate and we want to remove the nitrate from the system. So we will calculate the selectivity coefficient of nitrate over the bicarbonate. Okay. So the selectivity coefficient for nitrate is around 4, right? From the table that we have already given in the previous slides, right? And similarly, the selectivity coefficient for bicarbonate is around 0.4. So we can say that the nitrate over bicarbonate is equal to 10. So the value of K for the nitrate replacing bicarbonates is equal to 10. Similarly, the nitrate replacing the chlorides comes out to be 4. So this is estimated that the nitrate replacing both bicarbonates and chlorides can be estimated as an average value of around 7. Okay. So we can say that when we are having the equilibrium conditions where Ce by C naught is equal to 1, that is our ion exchange is completely exhausted. So in that case, the X nitrate which is present, so basically this is the fraction of nitrate which is present in the solution. So this is equal to 0.91, that is we can see here that we are having 0.91 of the nitrate present in the solution divided by the total ions present in the solution, that is 8.11 equivalents per liter. Okay. So this is fraction of the nitrate present in the water. So as we have discussed already that we can calculate the fraction present in the water and present in on the resin by using this equation for the monovalent ions. So we can replace here, this value is known to us, that is this value we have already calculated as 7, right? And divided by the fraction present in the wastewater. So this can be calculated from here. So this X bar can be calculated, but that is what is the fraction of the nitrate which is there present on the ion exchange resin. So around 47% of the exchange sites, they are basically helpful in the removal of the nitrate, right? Okay. So we know that the 2 equivalents per liter is the total capacity of the resin. So into the 47% that is there for the nitrate removal. So we know that the capacity, the limiting operating capacity in this case for nitrate, when it is present in combination with bicarbonates and chloride, it is around 0.94 equivalents per liter. Right? And then we can calculate, similarly we can calculate that what is the amount of water that can be treated by this type of resin. Okay. Because we know that the nitrate removal capacity of the resin, right? And we know that what is the solution of the uh, what is the concentration of nitrate in the solution. You can calculate what the amount of water that can be removed, right? So now the next case becomes, that is when the wastewater is having both sulfates, chlorides, and nitrates. So first of all, the sulfates can also remove bicarbonates and chlorides and nitrate. So we have to calculate first of all that what is the percentage fraction of sulfate which is present onto the ion exchange resin. So we can calculate in a similar way that what are the selectivity coefficient of sulfate replacing bicarbonate, sulfate replacing chloride, sulfate replacing nitrate. So these are the things, these are the values of the selectivity coefficient for all these three cases. Right? So we can calculate that sulfate replacing the nitrate, bicarbonates as well as chloride. So this can be estimated to be the average values of these three values. So the sulfate present in the solution we can calculate as 0.2 depending upon what is the concentration of sulfate in the solution divided by the total ionic concentration in the solution. And we can then use the equation which can be used for the divalent ions replacing the monovalent ions, right, in this case, and we can calculate the values of X here, for example, the solution sulfate present in the solution. Okay. We can put it here and we can calculate the sulfate present onto the ion. So you can see here that the sulfate now occupies around 68% of the exchange sites. Right? So now only 32% of the sites are left where we can have the replacement of nitrate and in competition with bicarbonates as well as the chloride. Okay. So now we can calculate what is the concentration of the nitrate present in the solution, and then we can calculate the selectivity coefficients for nitrate replacing bicarbonates, now nitrate replacing chlorides, and then we can calculate the average K values, right? And now we can also calculate based on this that what is the concentration of the nitrate present in the solution, what is the selectivity coefficient for the nitrate replacing the bicarbonates and the chlorides, and we can calculate now what is the fraction of our nitrate which will be there on the resin, right? Okay, okay, occupied by the nitrate. Okay. Now we know that only 32% sites were left after the sulfate have occupied the sites. So only 32% sites are left for our nitrate. So we multiply it because in competition with the chlorides and sulfate, only 0.5, that is 50% will be occupied by nitrate. So 50% of the 32% will give us around 16% of the sites are now being occupied by the nitrate, okay, in presence of our sulfate, right? So you can see that the capacity has reduced a lot. So around 0.32 equivalents per liter of resin is the limiting operating capacity, and we can now also calculate that we can only treat around 395 liters of water per liter of resin in comparison to the earlier case where we can treat around more than 1000 liters of water per liter. So we stop here and we'll continue our lecture in our next module. Thank you very much.